Okay, let's look at this lovely hot air balloon question from November 2021. This hot air balloon question has a lot of similarities to one of the supplementary papers, February-March 2017. So if you want to go and check out February-March 2017 for more hot air balloon practice, go ahead. For now, let's look at this one. It says a hot air balloon is moving upwards at a constant, unknown speed. So now, if anything is traveling at a constant speed, we know that our acceleration is 0. So it says to you, is the hot air balloon in free fall? So you know an object that is considered to be a projectile is considered to be in free fall. So free fall and projectile motion are very, very similar terms, okay? And if you go to the exam guidelines tell you that free fall is motion during which the only force acting on an object is the gravitational force. And we know from Newton's laws that F equals ma. So if the only force working on it is the gravitational force, this is where we get the acceleration is equal to g is equal to 9.8 meters per second downwards to the center of the earth. So we've just discovered from the question, it says that the balloon is moving at a constant unknown speed. Constant speed, if we are moving at a constant speed, there is no net force because there is no acceleration. But we know that an object that is in free fall has to be accelerating because gravity is working on it. So the balloon is not in free fall, no. And we should use the definition to help us answer the question. The balloon is not in free fall, no. There is another force acting on the balloon. Okay. Because how do we know this? We know this, we can add this to our answer. There's another force acting on the balloon because the acceleration is 0, not 9.8 meters per second downwards. Okay, so try and use the definition in your answer and say, no, we're not in free fall because there's another force. Or you can say gravity is not the only force acting on the balloon, something like that, so that you've got the definition and you've reworded the definition so that you have the answer with all the facts in it. Now it says to you, when the balloon is 200 meters above the ground, a small stone A is dropped from the balloon. See the diagram above. Another small stone B is dropped 5 seconds later from the balloon while the balloon is still moving upwards at a constant velocity. So we know this balloon is going upwards and the stone is going downwards. Okay. It says stone A strikes the ground at a speed of 62.68 meters per second. So when the stone gets down here, it's traveling at 62.68 meters per second. Okay. That'll be its final velocity on the ground for stone A. Now it says, ignore air resistance. That's how we can treat the stone as a projectile. The hot air balloon is not a projectile, but the stone is. And it says to you, calculate the speed of the hot air balloon. And you might be going, but how? I don't know anything about the hot air balloon except that it's a constant speed. We know that if we drop an object, normally if a question says, a stone is dropped. We usually use, when the word is dropped is used, we say that our initial velocity is 0. But if you think about traveling in a moving car and you throw something out the window, which you shouldn't because people shouldn't litter, that thing that comes out the car is traveling at the speed of the car as it leaves your hand because everything in the car is traveling at the speed of the car. The same thing with this little rock in the hot air balloon. When the rock comes out of the hot air balloon, it will initially be traveling at the same velocity as the hot air balloon. You're not adding another force other than the balloon to it to make it like to be thrown. You're dropping it out the balloon, but because the balloon is in motion, the stone is also in motion, and the VI of the stone is going to be the velocity of the balloon. Okay, so we can use the information given about stone A and we can use it to calculate the speed of the hot air balloon because the initial velocity of the stone is the same as the velocity of the hot air balloon. So if we look at stone A, what do we know? We know that the final velocity is 62,68. Okay, but before we do anything with this, we need to say, declare a sign convention. So I'm going to go up is positive, just because it's easier. At the moment, we're going to look at everything that's moving downwards, but a lot of people work with up is positive all the time. So let's just work with up is positive all the time. So we know that the final velocity of the stone is 62,68 meters per second, but it is downwards. So if up is positive, this will end up with minus 62,68. If we say how far has the stone traveled, delta y, the stone travels 200 meters to the ground, but is it 200 meters upwards or is it 200 meters downwards? It's 200 meters downwards, so it is now negative 200. We know the acceleration of the stone is going to be negative 9.8 because the stone, unlike the balloon, is a projectile. So if we know these things, we can use which equation is easiest. We are looking for what? We are looking for VI. So we know VF, we know delta Y, we know A. So let's use VF squared equals VI squared plus 2A delta Y. Okay, and we're using stone A to find the balloon. So my final velocity is going to be negative 62,68 squared is equal to my initial velocity squared, which is what we are looking for, plus 2 times negative 9.8 times my delta Y, which is negative 200. So if we put all this in our calculator, we end up with something like 392878, because that's going to become positive when we square it, equals VI squared. And now the sign of this is important. This becomes plus 3,920 because I've got two negatives there. So if we do the maths, we end up taking the square root of 8,78. So VI is 2,96 meters per second, and we are going to use the positive root because it's traveling upwards. So the speed of the hot air balloon, to answer the question, always make sure you've answered the question, the speed of the hot air balloon, and it says speed, not velocity, so we don't have to give it a direction, is 2,96 meters per second. Okay, now it says, how long does it take stone A to hit the ground? So let's have a look here. We want to check how long does it take for stone A to hit the ground. Let's rub out part of this and we can, I'm going to leave that speed of the hot air balloon there for now, and we're going to write on top of it in another color so that we can see what's going on here. So it says the time it takes stone A to hit the ground. Well, that's fairly straightforward. We can use things we know. We can use that we've just calculated this VI, and we have a VF, and we have a delta Y. So we can actually take quite a strong pick of equations that we want here. So let's just use the simplest one, VF equals VI plus A delta T. My final velocity was 62,68 downwards. Remember, we're still using up is positive. My initial velocity was 2,96 upwards, so it's positive, plus negative 9.8 times by delta T. So you end up with delta T equals something like 6,698 if you do the algebra. Yes, so I take this 2,96 over, subtract it, divide by 9.8. Let's round our answer. We get 6,70 seconds. Okay, so that is how long it takes stone A to hit the ground. Now, this part gets a little bit tricky. Okay, so it says to you, calculate the distance between the hot air balloon and stone B at the instant when stone A strikes the ground. So now we know, let's rub out some of the stuff on the balloon here. We know that stone A traveled downwards, okay? And we know that the balloon kept going upwards after stone A left, and then 5 seconds after stone A was dropped, stone B was dropped. So if we want to calculate the distance between the balloon and stone B, we need to find out how far did stone B will be dropped from a higher height, stone B, how far did stone B go down, and in that same time, how far did the balloon go up? Okay, so the most important thing here is to know the amount of time both of these have been traveling for, because obviously the balloon going up and the stone going down, they will have been traveling for the same amount of time. And then they said to you, when stone A strikes the ground. So stone A strikes the ground, it takes 6,70 seconds to go downwards, okay? But it says to you in the question, stone B is dropped 5 seconds later. So if stone B is dropped 5 seconds later, my change in time for stone B is going to be 6,70, which is how long stone A traveled for, minus 5. So stone B will only have traveled for 1,70 seconds, okay, which also means that the balloon will have traveled for, I can't write the whole balloon thing here, 1,70 seconds. So from now on, we can ignore anything about stone A. The only thing we needed to know about stone A was how long did it take stone A to get to the ground, 6,7 seconds, and then how long had stone B been traveling by the time stone A hit the ground, and that was 1,7 seconds, 6,7 minus 5. Okay, so now we need to think about our displacement here again. The balloon is going to displace up. This will be positive. And stone B is going to displace down. This will be negative. But if we want to work out the whole distance, we will have to add them together, because at the end of it, the balloon will be up here and the stone will be down here when they're separated at this point. Okay, so let's think what we know about the balloon. The balloon is easiest. Okay, what do we know about the balloon? We know that the balloon has got a VI, which is equal to the VF, because A is 0, because it keeps traveling at a constant speed. Okay, so we worked out what was the initial speed of the hot air balloon in 3.2.1. So this one is going to be 2,96. It's going to be VI and VF, and it's positive because it's going upwards. So if we want to know how far the balloon has traveled, we can use this equation, delta y equals VI delta t plus a half a delta t squared. So now we're looking at the balloon here first of all. So what is my displacement of the balloon? It is going to be 2,96 times by how long it's traveling, which is the same as the stone, 1,7, plus, now remember my acceleration of the balloon is 0, okay? So that handily gets rid of my t squared term. So I end up with something like 5,032 meters, and this is positive, it's upwards. So from the time they separated, this balloon went 5,032 upwards. Okay, so that's the balloon. Let us now go and have a look at stone B. What do we know about stone B? We know that stone B had an initial velocity that is the same as the balloon. Remember, stone A and stone B both have the same velocity as the balloon when they are released. Even if they drop, they have the velocity of the balloon. So the initial velocity is going to be 2,96 upwards. My change in time is going to be the same as the balloon, 1,7. And then we can just use, and now it's accelerating downwards, minus 9.8, because the stone B is a projectile, but the balloon is not. So if we use that exact same equation again, delta y equals VI delta t plus a half a delta t squared. This one's a bit more tricky because we can't get rid of anything with a 0, but it's not that much more tricky. So we've still got this 2,96, was it 2,96? 2,90, 2,96. Look, I forgot to put the 6 here because I can't read my own handwriting. And then 1,70 seconds plus a half, negative 9.8, and then no space, 1.7 squared. So if you put that all in your calculator, the initial velocity that it got from the balloon, the 1.7 seconds, the acceleration is 9.8 downwards, you end up with a displacement of negative 9,129. And you might be thinking, why have I got a negative number? Well, it's because we said up is positive and the stone was going downwards. So this is 9,129. So if we want the distance between the two, we have to add them together. How much the stone went down plus how much the balloon went up. So the distance between stone B and the balloon is going to be 5,032 plus 9,129, and if we put that in our calculator and we round it to 2 decimal places, we will end up with 14,16 meters to 2 decimal places. So altogether this is going to be 14,16 meters apart. Okay, so now let's look at the last part of the question here. Let's look on a clean drawing here. Okay, it says to you in 3.3, on the same set of axes, draw position time graphs for both the hot air balloon and stone A from the moment the stone is dropped until it strikes the ground. Use the ground as zero reference. Label your graphs balloon and A. Now this one doesn't ask you to put times on it, and it's for 4 marks. So I'm not entirely sure where all the 4 marks are coming from. But let's first think about this. When in grade 10 you start learning about displacement time graphs, okay? A displacement time graph for a projectile, I always say it looks like the shape of the motion of a ball if you bounce it. So like a bouncing ball ends up with a displacement time graph that looks like this, okay? So I always say it's a curvy shape. If somebody drops a ball off a building, a little man like this, and he drops the ball off the building, the ball goes down like that, and it looks like the bouncing ball curve, okay? So a projectile displacement time graph will look like a curved shape. So if we draw our axes here, and they say the ground is the zero reference, okay, we can't go below ground, so we know we're not going to have a negative axis, okay? So my displacement y is on the y-axis, and my time in seconds is on the x-axis. So the easiest one, if you practice this, is the stone A. And so stone A starts out here. If this is 200 meters, my displacement of 200 meters, it goes from 200 meters all the way down to the ground. And it's going to make that curved shape where initially it's going quite slowly and displaces only a little bit per unit time, and then as it falls for longer, the acceleration makes it have an increasing displacement per second. So it ends up with a curve that looks like that, which kind of looks like a bouncing ball. So that it's not quite like that, but it's like, gets a lot more vertical. Okay, so the thing is here, you can see I've lifted fractionally above 200 meters, and it's really exaggerated on this graph, because if you think about it, this ball left the balloon at a speed of what? The balloon and the ball were traveling at 2,96 meters per second. So the ball would have been traveling upwards, stone A, sorry, not the ball, stone A would have been traveling upwards for a teensy-weensy fraction of a time because it had an upwards velocity. It'll be like less than a second it was going upwards for. So there will be a fractional displacement above 200 here, and it's a bit exaggerated in what I've drawn, but technically it must be a little bit up, and then it's just going to come down I'm really bad at drawing these curves. You just have to bear with me. And then, okay, so the stone A is going to make this curve like this, fractionally up above the 200, and then straight downwards, accelerating every second. Mind this kink in here. Okay, you get the picture, yes? I'm very bad at drawing these, but it's this curvy shape like this. Okay, now, the second thing is, what is happening with the balloon? The balloon is traveling at a constant speed. So if you think back to grade 10 and all those questions with the trains departing the station and everything, object that is at rest, the displacement time graph is a straight line like this. The object never ever gets further away from where it is. The graph for an object at constant velocity is a straight line, and the graph for an accelerating object is a curve like this. So the balloon is this one in the middle. It is the one that is moving at a constant velocity, and it's moving at a constant velocity upwards. So it's always getting further and further from the Earth. So it is going to be a straight line drawn with a ruler heading upwards like that. If you want to, what you can do is you can put some times on here. You know that it took 6,7 seconds for the ball to hit the ground. And if you did some maths, you could figure out, if you used it previously to figure out how high the balloon was, you could have put that displacement on there as well, because you know you had to work out some stuff for stone B, but I don't think they want that. They didn't ask you to put times on it. But this is basically how the graph looks. We should label it. This is stone A, and this is the balloon. And notice I haven't given a very steep graph to a very steep gradient to my balloon graph, because it's going really slowly, 2.96 meters per second compared to how fast stone A was going when it hit the ground. It doesn't need a very steep slope.